Hello everyone, welcome to EGN 3343. This is Thermodynamics, and today we're going to continue our discussion on ideal gases. Remember that ideal gases are basically the same thing as substances. It's the same compressible pure substances that we talked about in lectures past, but with the characteristics that they operate at a much farther region of the saturation dome, so that under normal conditions they will never reach saturation. They will always exist in gas form or in vapor form, like it's the case, for example, for the 6 ideal gases that are under consideration in this class: air, nitrogen, oxygen, CO2, CO, and hydrogen. Those normally exist as vapor, as gases. We normally, their normal existence or their normal state is as a vapor. We know oxygen is a gas, we know hydrogen is a gas, we know CO2 is a gas, and CO is a gas. That doesn't mean that they cannot change phase to a liquid or even a solid. We know that we can actually liquefy or condense oxygen at very, very high pressures and very, very low temperatures. But under normal circumstances, they operate way out there, far away to the right of the saturation dome, and they will never actually, they will not condensate under normal conditions. Now, when that is the case, when we can assume that a substance can behave as an ideal gas, then things actually behave pretty nicely. The properties of the substance, or the gas in this case, responds to the so-called equation of state, where the where the product of PV divided by T, or the factor PV divided by T, remains constant. And in this case, that constant of proportionality, PV divided by T, equals to R. R is the gas constant. It's a gas constant that is tabulated for every single gas, or we can actually calculate it through the universal gas constant. We went through this explanation on the previous lecture. We can also express this equation of state in terms of the absolute volume, not necessarily the specific volume, but the absolute volume, knowing that the specific volume is the total volume divided by the mass. So pressure times volume is equal to the mass times R times T, where R is the particular gas constant. So every gas, air has a different constant as hydrogen, has a different constant as CO2, and so on and so forth. We also studied the relationship of the other two properties of the state, energy and enthalpy. So these relate the 3 fundamental properties: pressure, volume, and temperature, and these relate the energy and the enthalpy to the temperature directly. And we also talked about the fact that in ideal gases, energy is only a function of temperature, and so is enthalpy, only a function of temperature. So in order for the energy to change, the temperature has to change, and vice versa. If the energy changes, the temperature changes. And in order for the enthalpy to change, the temperature has to change. Okay? And vice versa. If there is no change in temperature, there's no change in enthalpy. There's 2 basic models for solving this particular integral. One is the constant or average specific heat model, where we can approximate CV to be a constant under this range of temperatures and say, well, that the change in energy is equal to CV times the change in temperature. Or we can just look up in the tables as a function of temperature only, the energy in state 2 and the energy in state 1, and subtract them. So we can look at the 2 values of temperature, the 2 corresponding values of energy. Same thing for the enthalpy. The 2 models are the constant specific heat model, constant or average specific heat model, where Cp times delta T equals delta H. Or you use the variable specific heat model, where you look up into tables and say delta H from 1 to 2 is simply H at T2 minus H at T1. We also looked at the relationship and defined, or actually derived the relationship, that R, the gas constant, is equal to Cp minus Cv. That's the specific heat at constant pressure minus the specific heat at constant volume. And also the ratio of specific heat K is defined as Cp over Cv. Now let's look at an example, and we're going to spend the whole lecture today working this example. And we are going to work this example using the 2 methods of calculating the energies and the enthalpy: the model of constant or average specific heats and the model of variable specific heats. And in this case, we have a cycle. We have a system that contains 2 kilograms of carbon dioxide, which is initially at 1 bar and 300 Kelvin. That's pretty much atmospheric conditions. 1 bar is about very close to the atmospheric pressure, and 300 Kelvin is about 27 degrees Celsius. It's very close to the regular standard atmospheric temperature. Now the system undergoes a power cycle. That means it's going to undergo a series of processes that is going to bring the 2 kilograms of CO2 back to the initial state 1, back to 1 bar and 300 Kelvin. The first process, we call it the process 1, 2, because it takes us to state number 2, is a process at constant volume. The volume is going to be the same in state 2, and the pressure is going to raise to 4 bar. So we are given the final pressure of this process, and we are told that this is an isometric or constant volume pressure, or constant volume process. Then the following process is an expansion from 2,3, process from 2,3 is an expansion that follows the curve PV to the power 1.2 equals to a constant. This is a polytropic process. And then the final process, there's 3 processes to close the cycle. Process 3 to 1 is a constant pressure compression or contraction. Constant pressure basically means that the pressure at 3 is equal to the pressure at 1. So this is telling us something about the pressure at state 3 is equal to the pressure at state 1. If this is a constant pressure contraction process, the pressure at state 3 is equal to the pressure at state 1. So the process from 2 to 3 takes us back to the original pressure of 1 bar, because the process from 3 to 1 is an isobaric process, a process of constant pressure. Okay, so this is the information that is given. We are to sketch the cycle on a PV diagram, and we are to calculate the thermal efficiency of the cycle. Remember that to calculate the thermal efficiency, you have to calculate all the heats, and you have to calculate all the works, okay, for every single one of these processes, including the one that returns back to the original state. So this is a closed cycle, and we are being told that this is a power cycle, and we are to also verify that whether this is really a power cycle, or is it a refrigeration cycle, or is it a heat pump cycle. The only way to know whether this is a power cycle is that the net amount of work produced in the cycle is positive. If the cycle produces work, then we call this obviously a power cycle, because we're using heat in order to produce work. If the net amount of work during the entire cycle is negative, then this is either a heat pump or a refrigeration cycle, because we're using work or power in order to refrigerate or heat. So we're assuming that this is inside a piston cylinder assembly, and that piston moves and compresses and expands and so on throughout the cycle. State number 1, we have a pressure of 1 bar, 300 Kelvin. Then we go an isometric process. So the volume at state 2, whatever is the volume at state 1 is the same as state 2. And we raise the pressure to 4 bar. Then we go through a process, a polytropic process, where PV to the 1.2 is equal to a constant until the pressure reaches 1 bar. So we go down in pressure. It's an expansion where the pressure goes to 1 bar. And we know that it goes to 1 bar because the process from 3 to 1 is an isobaric process. We're told that the process from 3 to 1 is a constant pressure process. So if we plot this in a PV diagram, which is pretty much the first thing you should do to be able to visualize what these processes are doing, we have the first process from 1 to 2 is a constant volume process. So it's a vertical line in the PV diagram. Volume doesn't change. Then from 2 to 3, we have this PV to the 1.2 equals to a constant. Remember, all of these are asymptotic curves. Depending on this exponent, the larger this exponent, the steeper this curve, but there's always going to be a concave curve. And it goes down, and it goes down to the original pressure of state 1. So this is state 3 right here. And then it closes the cycle by returning to the original state at a constant pressure process. So this last line has to be horizontal. Now, because this process goes in a clockwise direction, it goes from 1 to 2 to 2 to 3 to 3 to 4, we know that the net amount of work produced in here is going to be positive. How do we know that? Remember, the work is the area under the curve. And in this case, the net amount of work is the area under all the curves. The area under 1, 2 is 0. Obviously, this is an isometric process, no work. The area under 2, 3 is positive. It's the entire area under this curve 2, 3. And the area under 3, 1 is negative because it's a contraction process. We're reducing the volume. But in magnitude, the area under 2, 3 is larger than the area under 3, 1, and therefore the net amount of work is positive. And this is indeed a power cycle. Okay, so let's summarize these properties that were given to us. State 1, we know the pressure and the temperature. We don't know the volume. We are told that the volume at 2 is equal to the volume at 1, and that the pressure at 2 is equal to 4. And we are given the pressure at state 3 is 1 bar, because we know that the process from 3 to 1 is an isobaric process. So this closes up the cycle, going from 3 to 1. All right, so what do we do with these? We have certain equations that we are allowed to use, certain tools that we can use in order to calculate what we need. We know that work is equal to the integral of PdV. We know that if there's no volume change, there's no work. We know that if the pressure is constant, we can take this out of the integral, so it will be P times the change in volume. We know that the state equation, because CO2 is an ideal gas, this always applies. PV is equal to RT. Or we can just say that the ratio PV divided by T always remains constant on any process. PV divided by T is always a constant on any process, regardless of whether the process is isometric, polytropic, isentropic, isobaric, isothermal. PV divided by T is always a constant. We know the first law of thermal, where the change in energy is equal to the heat minus the work. And notice that I am writing all these in specific form, with lowercase variables, specific forms. And the efficiency of the thermodynamic efficiency or thermal efficiency of a power cycle is the amount of work, amount of net work being produced in the cycle, Wn, divided by the amount of heat that we put in. Not the net amount of heat, but the amount of heat, only the positive amount of heat. Because throughout these processes, there's some heat that is being put in and then some heat that's being rejected, some waste heat. We don't take that into account when calculating the efficiency. Okay? It's only what you obtain out of the cycle, which is the net amount of work, divided by what you put into the cycle in order to produce that work. And this, the cost of producing work, in this case, is the cost of fuel or whatever it is Qn. All right. So, and here's the PV diagram, which we already drew in the previous case. Remember, clockwise means that this is a power cycle. You can also deduct that from the fact that the net amount of area here is positive, because the area from 2 to 3, which is an expansion process, is positive. The area from 3 to 1 is negative, but the area from 2 to 3 in magnitude is larger than the area from 1 to 3. So at the end, you're going to have a positive amount of work, and we're going to calculate that. Now, what do we know about these gas? This gas is CO2, which has a molecular weight of 44 kilograms per kilomole. And why are we finding the molecular weight? Well, because this way we can calculate the gas constant. The R of CO2 is the universal gas constant divided by the molecular weight of the specific gas that we're using. 8.314 is the universal gas constant. If we divide it by 44, we get 0.189 kilojoules per kilogram Kelvin. So that is basically the gas constant that we're going to use in all of our equations of state, because we're dealing with CO2. Let's calculate the volume at state 1. If we go back to the summary of conditions or summary of properties, according to the state postulate, if we have two properties, that means that we have everything we want in that state. So we know the pressure and the temperature in state 1. That means that we can know everything else that we want. We can know the volume, the energy, the enthalpy, and anything else. So we're going to use that pressure and that temperature with the equation of state, knowing that R is equal to 0.189. Now that we know R, the volume 1, specific volume, according to the equation of state, is RT1 divided by P. That comes directly from PV equals to RT. Now that is 0.189 kilojoules over kilogram Kelvin times 300 Kelvin divided by 1 bar. But we need to actually convert that pressure into a pressure that will actually be consistent with the rest of the units here. 1 bar is equal to 100 kilopascals. And 1 kilopascals is 1 kilojoule divided by meter cube. Same thing. Remember that a kilopascal is a newton or a kilonewton over a meter square. And a kilojoule is a kilonewton times a meter. So a kilopascal is the same thing as saying 1 kilojoule over meter cube. So this kilopascal and this kilopascal cancel out, this bar and this bar cancel out, and basically 1 bar is equal to 100 kilojoules over meter cube. That way we can cancel the kilojoules, we can cancel the Kelvin, and what we'll end up with is meter cube on the numerator and Kelvin and kilogram on the denominator. The specific volume at state 1 is 0.567 meter cube per kilogram. So we have now defined state 1. We have pressure, temperature, and volume. Let's stick now with the fundamental properties: pressure, temperature, and volume. We have pressure, temperature, and specific volume. So what do we know about state 2? Well, we know that the volume in 2 is equal to volume in 1. We were told that this is an isometric process, a constant volume process. Since we know the volume and we know the pressure is now equal to 4 bar, we can calculate the temperature. We can either do that through the equation of state. We can say P2V2 equals to R2, It will be exactly the same thing. Now that we know P2 and V2, P2 is equal to 4 bar, V2 is equal to that V1 that we just calculated, and we can just solve for T2 directly from state 2. Or we can relate state 1 and state 2, just like that. It's P1 V1 over T1, that's equal to R, and R is also equal to P2 V2 over T2. We can solve for T2 from here, and it's equal to T1 times P2 over P1 times V2 over V1. T1 is equal to 300 Kelvin. The ratio of P2 over P1 is 4 bar to 1 bar, and the ratio of V2 over V1 is 1 because the volume doesn't change. So that means that the temperature in 2 goes up by a factor of 4, so it's 1200 Kelvin. So now we have pressure, temperature, and volume in state 2. Now let's go to state 3. In state 3, we know that the relationship P2V2 to the 1.2 equals to P3V3 to the 1.2. We know that the relationship PV to the 1.2 equals to a constant on that process from 2 to 3. Okay? Since we know P2, we know V2, and we know P3 because P3 is back to 1 bar, we can calculate V3. So V3 is equal to V2, solving from this equation, times P2 over P3 to the power of 1 divided by 1.2. And what we get out of these is that V3 is equal to 0.567, which is the volume at state 2. Pressure at 2 is 4 bar, pressure at 3 is 1 bar. To the power of 1 over 1.2, that is about 0.83, that power. So it's 4 to the power of 0.83 times 0.567 is equal to 1.8. So the volume went up from 0.567 to 1.8 in the process from 2 to 3. So now we have pressure and volume in state 3. What else do? We need the temperature. We can relate the temperature between the same way we relate anything with the state equation. P2V2 over T2 is equal to R. R is also equal to P3V3 over T3. That is the equation of state. So from here we can solve for T3, or we can just simply use V3 and P3 in the equation of state and say that that's T3 is equal to P3V3 over R. It's up to you. So T3, solving from here, is equal to T2 times P3 over P2 times V3 over V2. So is 1200 Kelvin, that's T2, times the ratio of pressures from 3 to 2, which is 1 bar to 4 bar, times the ratio of volume from 3 to 2, which is 1.8 to 0.567 cubic meters over kilogram. And that gets us to a temperature of 952 Kelvin. So now everything is defined in all three states in terms of fundamental properties: pressure, temperature, and volume. We have pressure in state 1, pressure is 1, temperature is 300, volume is 0.567. State 2, pressure is 4, temperature is 1200, volume is 0.567. And state 3, pressure is 1, temperature is 952, and volume is 1.8. And then this goes back to 0.1. Okay? All right. Now let's calculate the energies and enthalpies. The other two properties are important in every single state so that we can later use them in the first law of thermo to calculate the heats and whatever else we need for the outcome of this problem. Now the energies and enthalpies for an ideal gas are only a function of temperature, whether you use the constant specific heat model or the variable specific heat model. So let's start by using the variable specific heat model. Let's use the tables. And in this case, we basically know that energy 1 is equal to the energy at 300 Kelvin, and enthalpy 1 is equal to the enthalpy at 300 Kelvin. That's the temperature of state 1. Energy 2 is equal to the energy at 1200 Kelvin, and enthalpy 2 is equal to the enthalpy at 1200 Kelvin. That's the enthalpy, that's the temperature of state 2. Energy 3 is equal to the energy at 952 Kelvin, and enthalpy 3 is equal to the enthalpy at 952 Kelvin. That is the temperature of state 3. All we have to do is go to this table. There's table A23, which is posted for you on D2L, which shows the enthalpies, the energies, and this value that we don't know what it is a form of entropy as a function of the temperature in Kelvin. So all you have to do is go in with temperature and extract what you need. One thing to notice, this, by the way, this table is only for CO2, CO, water vapor, which can also act as an ideal gas at very, very high temperatures, and O2 and N2. Okay, it doesn't have hydrogen, it doesn't have air. There are specific tables for air. We know we already used those. But more importantly, what you see on this table is that you don't get U or H. You get U bar and H bar. Look at the units. The units are in kilojoules per kilomole. Instead of kilojoules per kilogram, you get kilojoules per kilomole. Okay? So we have to be careful with that because we have to divide these values by the weight, by the molecular weight of the specific gas in order to get kilojoules per kilogram. For some reason, table A23 is the only table in the entire book that is expressed in terms of kilomoles instead of in terms of kilograms. So this is what we're going to do. State number 1 is at 300 Kelvin. And here's the energy, 6939, and here's the enthalpy, 9431. But that is in kilojoules per kilomole. So at 300 Kelvin, the energy is 6939 kilojoules per kilomole. We divide that by 44 kilograms per kilomole. The kilomole and the kilomole cancel out, and we get 157.7 kilojoules per kilogram. Same thing we do with the enthalpy. At 300 Kelvin, 9431 divided by 44 is 214.34 kilojoules per kilogram. So now we have energy and enthalpy at state 1. Let's go to state 2. State 2 is 1200 Kelvin. We go to the other part of the table, the one that reaches 1200 Kelvin. Notice again, this is in the units of kilojoules per kilomole. We looked at the first column because that's CO2. The other one is CO. The other one is H2O, O2, and 2, so on and so forth. Energy is 43,871. Enthalpy is 53,848. So, energy 2 is 1200 at 1200 is 43,871 divided by 44 is 997.07 kilojoules per kilogram. Enthalpy 2 is the enthalpy at 1200 Kelvin, which is 53,848 divided by 44, the molecular weight, 1,223.82 kilojoules per kilogram. So we have completely defined state 2. Temperature, pressure, volume, and now energy and enthalpy. By the way, again, this is using the variable specific heat model. And the third temperature state 3 is 952. Obviously, there's not an entry exactly from 952. There's an entry for 950 and an entry for 960. So somehow we have to interpolate between this value. The value of energy will be somewhere between 32,171 and 32,625. And the value of enthalpy will be somewhere between 40,070 and 46,07. Okay? How do we interpolate? Well, we know that this one is at 950, this entry is at 950, and this entry is at 960. And our value of temperature is 952, which is 20% of the way between these two brackets. Okay? So, in this case, energy at 952 is the interpolation between 32625 and 32171, or better said, between 32171 and 32625. The interpolation is going to take a slope of 952 minus 950 divided by 960 minus 950, basically 20% of the way between the bracket of 960 and 950. And that we add to the lower bracket of the energy, which is 32171. This is basic interpolation. We've done it in with the other tables when we were looking at substances and air. We divide that by 44, which is the molecular weight, and at the end we get 733.22 kilojoules per kilogram. Same thing for the enthalpy. At 950, the enthalpy is 40,070. At 960, the enthalpy is 40,607. So we interpolate between these two values at a rate of 952 minus 950 divided by 960 over 950. Notice that this ratio here gives you exactly 0.2, 20%, which means 20% from the lower end of the bracket. So we're going to get a value that is 20% above 40,070 and between 40,070 and 40,607. Once we divide that by 44, we get 913.12 kilojoules per kilogram. So now that brings us to a full table of the state properties. In state 1, we have pressure, temperature, and volume. Now we have energy and enthalpy in kilojoules per kilogram. In state 2, we have pressure, temperature, and volume, energy and enthalpy. And in state 3, we have pressure, temperature, and volume, and energy and enthalpy. Everything. So we have everything we need. Now it is a matter of applying the first law of thermal at every single process. We're going to go on the process from 1 to 2, on the process from 2 to 3, and the process from 3 to 1. Calculate the work, calculate the heat, summarize that in a table, and then calculate whatever we need, such as the thermal efficiency. All right, so let's go now through the processes. We define every single state, 1, 2, 3. Now we have to look at the process from 1 to 2, the process from 2 to 3, and the process from 3 to 1 to close the cycle. Remember, this only happens because it is a cycle. Otherwise, we don't have to close the loop. Now, the process from 1 to 2, the work is equal to 0. Work from 1 to 2 is equal to 0 because it's an isometric process. The change of energy from 1 to 2 is basically energy 2 minus energy 1, which we can look up in the table that we just filled out. 997.07 minus 157.7 gives us 839.37 kilojoules per kilogram. And the heat, according to the first law of thermo, remember, heat is equal to change in energy plus work. Change in energy is 839.37. We just calculated here. The work is 0. The heat from 1 to 2 is a positive amount of heat at 839.37. So that's heat into the CO2. We're adding energy to the CO2 by whatever means. Process from 2 to 3. This is the process that follows that curve, the polytropic curve. P times V to the power 1.2 equals to a constant. And we know that for those processes, the area under the curve is given by P times V minus P times V divided by 1 minus N, where N is equal to 1.2. So we have P3 equals to 1 bar, volume 3 equals to 1.8 meter cubes per kilogram, P2 equals to 4 bar, V2 equals 0.567. 1 minus N is equal to 1 minus 1.2. We have to change those bars to kilojoules divided by meter cube, or basically 1 bar times a meter cube is equal to a kilojoule. It's equal to 100 kilojoules. It's the same logic. 1 bar is equal to 100 kilopascals. Those are 2 units of pressure. And a kilopascal is equal to a kilojoule divided by a meter cube. And this leads to 234 kilojoules per kilogram. That's the amount of work generated in the process from 2 to 3. Notice that it's a positive amount of work because it's an expansion process. Also, the energy changes from 3 to 2 because the temperature changes from 1200 to 952. And we should expect a negative change in energy because the temperature went down, obviously. So energy at 3 is 733.22 from the table. Energy at 2 is 997.07. The amount of energy lost in this process is minus 263.85. So energy went down. First law of thermo again. Heat is equal to delta U plus work. Or seen the other way, delta U is equal to heat minus work. Okay, I'm calculating the heat. Delta U is minus 263.85 and work is 234. And that gives us a net amount of work in this process from 2 to 3 of minus 29.85. So this is heat rejected, heat waste. So the CO2 is losing heat to the atmosphere, to the surroundings, at a rate of 29.85 kilojoules for every kilogram of CO2. Notice that I'm using everything in specific form, lowercase w, lowercase q, lowercase u. I don't need the 2 kilograms, I don't need the mass yet, because everything I can do in specific form, and later on if I need to do so, I can calculate things in total form. Finally, the process from 3 to 1. This is the process that closes the loop. This is a process that goes back to state 1. This is an isobaric process. So the work is simply pressure times the change of volume. The pressure doesn't change, so it comes out of the integral. Every time you have an isobaric process, work is equal to P times delta V. The final volume is V1, the initial volume is V3. Remember that we're going from 3 to 1, so final is 1, initial is 3. Pressure is 1 bar. Volume goes from 1.8 to 0.567, so this is a contraction process. We expect a negative work. Again, the conversion of bars to kilojoules over meter cube. We get minus 123.3 kilojoules per kilogram. That is definitely smaller in magnitude than the previous one of 234. That's why the net amount of work is going to be positive. The positive work is larger than the negative work in the cycle. Delta U from 3 to 1 is a change of energy. 157.7 divided by 7 or minus 733.22. That's minus 575.52. Obviously a negative amount of energy change because the temperature went from 952 at state 3 to 300 Kelvin in state 1. And therefore we can calculate the Q. The Q is delta U plus W according to the first law. Delta U is 575.52 negative. Work is minus 23.3. That gives us a net amount of work in the process from 3 to 1, negative 698.82. So this is rejection of heat waste to the atmosphere. This is nothing. In this process from 3 to 1, we're not putting fuel in, we're not injecting heat into the CO2, we're letting the CO2 release energy over to the atmosphere. By the way, we can do this alternatively. Remember that for isobaric process, the change of the heat is equal to the delta H, to the change in enthalpy. Only for isobaric processes. Heat is equal to the change in enthalpy. So H1 minus H3, which we have from the table, gives us 698.72, almost identical. In theory, it should be identical because that's how enthalpy is defined in terms of energy and PV. But there's errors there in the fact that we went into a table and interpolated and so on, and that's just noticeable there in the 4th decimal place. Okay, but that's an alternative to calculate the heat from 3 to 1 if you need to. So back to a summary of processes. Basically, we have a process from 1 to 2 where there's no work and there's a heat in of 839.37. We have a process from 2 to 3 where there's positive work because it's an expansion process. Maybe this piston is moving up or expanding. And we have an energy release in the form of heat or heat waste of 29.85, negative. And then the process from 3 to 1 that brings us back to the initial state is a process by which it's a contraction process, that's the work is negative 123.3 and the heat is negative 698.78. So there's also heat waste. So we can calculate the net amount of work as the sum of all works, 0 plus 234 plus minus 23.3. We get positive amount of 110.7 kilojoules per kilogram. Okay? So this tells us that this is indeed a power cycle because the net amount of work produced in the entire cycle is positive. We have to disseminate between the heat that was put in and the heat that was released or wasted. According to this table, the heat that was put in is only in process from 1 to 2, and that's 839.37. And the heat waste occurred in process 2.3 and in process 3.1. So we can calculate Q out as Q23 plus Q31. So Q out is the sum of these two, which is minus 728.63. The sum of these two. So we have W net, we have Q in. That means that we can very easily now calculate the thermal efficiency. Thermal efficiency is W net, whatever you obtain from the cycle in the form of work, divided by whatever you put in terms of fuel. In this case, 839.37 is what you put in. Not what you wasted, but just what you put in. And in this particular case, only in this particular case, the positive heat, Qn, was found in process 1-2. We can have another cycle where that could be found in another particular process. But in this case, it was only in the process 1-2. The ratio of these two is 0.132, which is 13.2%. So what does this mean for this particular cycle? It means that 13.2% of the energy that we put in the form of heat by burning a fuel or whatever was actually used into making power. That means that we wasted about 87% of the energy. And that's not very uncommon. That's actually what happens in reality in internal combustion engines. You usually waste about 80% of the energy that you put in. But that's okay because the caloric content of the hydrocarbons that you use to actually release energy in the form of heat is very high, have a lot of caloric density, so you can actually afford to waste a lot of energy. In this case, we're wasting almost 87%. By the way, the thermal efficiency can be calculated alternatively. It's actually the same equation. We went over this in the previous lecture. It's 1 minus the heat waste divided by the heat in. And that should give you exactly the same result, 13.2. Q out, we use the absolute value, 728.63 divided by the Q in, the amount of energy put into the system, 839.37, gives you the same thing, 13.2%. The efficiency of a cycle, of a power cycle, can never be over 100%. We'll actually be pretty lucky if you reach 50%. Okay? Only in very few instances you reach about 50% efficiency. And very, very efficient power cycles. All right, so let's go back now to the table where we completed the fundamental properties, pressure, temperature, and volume. And instead of calculating energy and enthalpy from the tables, let's use the alternative method in which we assume that the specific heats in every single one of these processes behaves as a constant or as an average value. So there's an average specific heat between 300 and 1200 Kelvin. There's an average specific heat between 1200 and 952, and an average specific heat between 952 and 300. So if this is the case, we have to go to table A20, in which we find the Cp and Cv for many ideal gases as a function of temperature. So as you can see here, carbon dioxide, you can see the Cp and the Cv, as well as the ratio of the two, which we don't need, as a function of the temperature at 300 Kelvin, at 700 Kelvin, at 1000 Kelvin, and so on and so forth. Okay, so what do? We go to the table. In the process from 1 to 2, where the temperature goes from 300 to 1200, the average temperature is about 750 Kelvin. That's this one plus this one divided by 2. The average temperature in the process from 1 to 2 is about 750 Kelvin. That means that if we go back to this table, at 750 Kelvin, we can find Cv approximately 0.959 and Cp 1.148. Notice the units kilojoules per kilogram Kelvin. So we write that down. Let's assume that Cv and Cp behave as average or constant between 1 and 2, and these are the values. Now let's go from 2 to 3. From 2 to 3, we have a temperature of 1200 and 952. The average is probably about 1070 Kelvin. Just about that. We don't have to be very precise when going to this table because this is a big approximation. We're making big assumptions by saying that the Cv is a constant. So might as well not be very precise when calculating average temperature and when looking up the table. So we're going to go to the table and look up about 1070 degree Kelvin, or 1070 Kelvin. Go back to the table. We notice that the table ends at 1000 Kelvin, so let's use the last values here. Instead of trying to extrapolate or do something fancy, let's just use 1.045 for Cv and 1.234 for Cp. That will be good enough. 1.045 for Cv and 1.234 for Cp. And in the final process, the process that goes from 3 to 1, temperature goes from 952 to 300. That means an average temperature is a temperature of about 626. We got to go to that table at 626. Obviously, there's not an entry for 626, so we pretty much do an eyeball calculation or interpolation between these two values. I would say that this is about 0.9 in between here, and I would say this is about 1.09 in between those two. So I wrote 0.899 for Cv and 1.088 for Cp. What do I do with these things? Instead of going to the table like I did on the previous method, on the variable specific heat method, for calculating energy and enthalpy, I calculate the change in energy and the change in enthalpy in every single one of these processes using the Cv and the Cp. Okay. By the way, when I assign a problem, you either use one of the method or the other method. You either use the variable specific heat method, which is the accurate method, or the constant specific heat method, which is the easy one, but the one that yields the most air. I am going to tell you what method to use. I'm going to tell you can assume that the specific heats are constant. By the way, in the test, I always let you use the constant specific heat method because it's simpler and it's faster. Because you don't have to do these interpolations on the table and so on. So let's do the alternative method in the process 1-2. The work still 0. That has no, the fact that the specific heats are constant has no relevance over the work. But the delta U can be calculated now as Cv times delta T. Where Cv from 1 to 2, we just wrote that on the table, is 0.959. The delta T is 1200 minus 300. That leads to 863.1. That is a major difference from before because the heat now, which is delta U plus W, is 863.1. Remember the previous table, the one where we used the variable specific heat? This was 839. So this yielded an error of about 20-something kilojoules per kilogram, which is pretty considerable. It's over 5% error, actually 4% error. All right, so now let's go for the process from 2 to 3. Well, the work, we don't need to talk about that because the work is calculated exactly the same way. We don't need to worry about how do we calculate the work. It's the same exact way, nothing changes. But the change of energy is now Cv times delta T. Cv in the process from 2 to 3 was 1.045. It actually raises considerably more. The change in temperature is 952 minus 1200. And the energy, therefore, the energy change is minus 259.16. Therefore, the heat, delta U plus W, comes up to be minus 25.16. Again, it's a waste heat, it's negative. But it's different than before. Before it was 29, now it's 25. Now in the process from 3 to 1, we have the work is the same way. It's an isobaric process, so therefore pressure times delta V leads to the work of minus 123.3. That doesn't change. The change in energy is CV times delta T. CV was calculated at 0.899 from the table. Delta T is 300 minus 952. That leads to minus 586.15. From the first law of thermo, delta U added to the work gives us a heat of 709.45. Again, released. Before it was 728, now we're at 709. So these are quite different numbers when we use this method. Or alternatively, we can do this using the fact that for isobaric processes, the heat is equal to the change in enthalpy. And we know that the change in enthalpy is Cp times delta T. Cp times delta T, Cp on the process from 3 to 1 was listed at 1.088. Temperatures 300 to 952. The amount of heat release is 709.38. Quite similar. So whether we use this or use this to calculate the heat makes no difference, as you can see. So let's now take these values and summarize it on a table. Now the works are the same on processor 1, 2, 2, 3, and 3, 1. 1 positive, 1 negative, and 1 0. And the heat, positive heat from 1 to 2, waste heat from 2 to 3, and waste heat from 3 to 1. That leads to the calculations again of the net amount of work. The sum of the works is the same, 110.7 kilojoules per kilogram. The amount of heat put into the system is 863.1 kilojoules per kilogram. And then the amount of heat waste is the other two because they are negative. They happen to be negative in this particular problem. It's minus 25 minus 709. That leads to minus 734.61. Now what's going to happen here is that because we made so many assumptions and assuming, again, sorry about the redundancy, that CV and CP behave constant on every single one of these processes, when we calculate the thermal efficiency, we're going to get different numbers. Before we got 13.2%, now we got 12.8% when we use W net over Qn. Okay? Now, it might not sound like much between 12.8 and 13.2, but that at 0.4% change in efficiency or error in efficiency is huge. Let's assume that this is part of a thermodynamic cycle that undergoes in a process of power generation in a power plant. And this Qn is 863.1 kilojoules per kilogram of air that you put into the power plant. Let's assume that this is a gas power plant. And let's assume that instead of 2 kilograms of air, we put in, I don't know, 2 million kilograms of air per week or per year, let's say. So we're talking about millions and millions of dollars in fuel savings or fuel difference that one calculation leads in error with respect to the other one. More importantly, when we calculate this thermal efficiency using the alternative way, which is actually the same formula, because W net is equal to Q in minus Q out, we should get exactly the same number. If these numbers were correct on the table, if these numbers were accurate, we should get exactly the same number for the thermal efficiency when calculated this way or calculated this way through any of these two formulas. And notice the discrepancy. 12.8 in this case, and in this case 14.9. This is telling me that there's a discrepancy in the way these things are being calculated. If you go back to the table, you'll notice that the discrepancy comes into the fact that the amount of net work should be equal to the amount of net heat. If you add all these heats, you should get exactly the same amount as if you add all the work. Because in a cycle, the change in energy is equal to 0. Because you go back to the initial state. The net amount of work is 110. And the net amount of heat, which is this one plus this one, notice is about 129. That's quite different than this one. So there's a major error when using the constant specific heat model. Nonetheless, we're going to allow you to use this one for efficiency purposes because it is faster, especially for tests. So This is the thermal efficiency. Which number do we trust? Actually, we cannot trust either one of them because these numbers come from not accurate approximations, but this is just an illustration of the methodology. So this is it. This is the discussion on ideal gases, and this is the implementation of the concepts of ideal gases into an example problem in which we went through many different processes in a cycle and calculated using the two models, the constant specific heat model and the variable specific heat model, and talked about the difference between the two. So thank you for your attention, and I'll see you next class. Goodbye.